Much, Claire. Yeah, so thanks very much for joining me here today. I probably won't talk that much about dark matter, so hopefully I'll tell you now so that you're not too disappointed later on. So I'll start with a few words on why forensic-like studies of galaxies, like we can do for our Milky Way, is really powerful for understanding the evolution of disk galaxies. How our understanding of the Milky Way has been completely revolutionized by the advent of the Gaia spacecraft. And finally, I'll touch on a few events that we think have shaped the outer disk and halo of the Milky Way. So I'm going to start very early on. So if we look at galaxies in the early universe, you can see on the left here, they look like rather featureless groups of stars. And somehow there's different paths of transformation that lead to them being becoming these rather regular array of morphologies. So they either fit into the spiral category of galaxies or the elliptical category of galaxies in the present day. So there are some kind of set pathways for evolution that create either an elliptical or spiral. And obviously there are other galaxies in between, but these are the two primary categories. So we know that the different evolutionary pathways, they consist of a number of things. So they consist of the formation of new stars, the death of stars. You also have dynamical interactions between stars, for example, in different components of a galaxy, like the spiral arms or the bars. And you also have the merger history. So these are collisions between galaxies, and together they somehow create the regular array of morphologies we see today. Now, there's lots of ways of trying to reveal the balance between the different processes that are important for the different kind of galaxies. So you have, on the theoretical side, you have numerical simulations of galaxy formation. So I've sort of shown an example here. And these are really amazing at following the clustering of dark matter at early times, the birth of the first galaxies, collisions between galaxies until the present day, and they've been really remarkable in recovering the large scale structure of the universe. Now, on the observational side, efforts can be sort of divided into two main camps. You've got observations of high redshift galaxies, where, for example, candles here, where you have the ability of observing hundreds of thousands of galaxies at different redshifts and different environments. So you can gauge how the morphology of a galaxy depends on redshift and environment. And finally, you have the observations of nearby galaxies. So for nearby galaxies, I mean galaxies for which you can essentially look at different points within a galaxy and learn something about the phase space distribution, the age and metallicity distribution of stars at different points. And so what's different about these nearby galaxies, so I'll introduce this function here and come back to it later, and so hopefully it's not as terrifying when I come back to it later. This is something I call a distribution function, which essentially depends on where the stars are in terms of their positions, what velocities they have, and also here I've looked at the metallicities, alpha abundances, and their ages. And this is really something we only have access to nearby galaxies. So for example, I've got an image here of a galaxy observed with MANGA. So here you've got an idea of how the stars are distributed, just looking at the brightness distribution here. And then at each point in this galaxy, you can also have a spectrum. And then if you analyze the shape of the lines in the spectra, you get information on the velocity distribution of the stars and also the velocity dispersion distribution of the stars. And this phase-space distribution of the stars essentially encodes the gravitational potential, and therefore there's information there on the black hole masses and the dark matter content. They also detail the orbital distribution of the stars. And this is really important to have access to because, for example, in the halo, which we think is mainly made out of stars that have been accreted by satellite galaxies like other dwarfs or perhaps globular clusters, you have some information about the type of system that's been accreted. So for example, if you have a very massive dwarf, this probably experiences significant dynamical friction on its approach to the central host galaxy. And the orbits within that galaxy end up being radialized. And so there's a signature in the orbital distribution of stars that come from these kind of galaxies. Smaller systems, on the other hand, the orbits of these galaxies are probably preserved somehow in the orbits of the stars when they've become part of the host galaxy system. The other thing we also have access to for these nearby galaxies, again, this is MANGA data, you can essentially obtain star formation history. So you have information on the metallicity at different points and how it's changed over time as well, because you have information on the age distribution in these galaxies. And these in turn encode the gas flow history and also interactions between galaxies, which themselves will impact on the gas inflow history. Now, for the Milky Way, we have access to phase space, metallicity, and age information for individual stars, not just for stars along the line of sight, like we did for the MANGA data, but actually for individual stars. And even before Gaia, we had ages for samples of stars that were maybe not so far from the sun, and this actually revealed quite a lot. So this is just a plot from a paper now, 20 years ago, actually, it's quite unbelievable. Just looking at the age velocity dispersion in the solar neighborhood. So on the y-axis, you've got the velocity dispersion, and on the x-axis, you've got age. And these are stars, just dwarfs and subgiants in the solar neighborhood that have parallaxes measured by Hipparchus, as well as apparent magnitudes and some spectra. And from these data, what you can see is a velocity dispersion that increases with age. So there's a gentle slope for about the first 9 gig years. 9 gig years looking backwards in time. And then for the older stars, there seems a steeper rise in the velocity dispersion. So if we just examine this bit in a little bit more detail, you can look at M-body simulations that were run by a number of people. I've just shown an example here from Mikhail Alma's work. So it's looking at how isolated disk galaxies embedded in live dark matter halos, how their velocity dispersion changes with time. And Mikhail attributes this increase to secular processes. So for example, here is the relation between vertical velocity dispersion and the ages of the stars. And so you have some heating, which is a result of interactions with spiral arms. And then you, especially in the vertical component, you also have this additional component, which is heating due to interactions with giant molecular clouds. Now, if we look at observations of cold gas, so this is actually from quite recent work. On the y-axis, you have the velocity dispersion of gas, and we're interested in the blue points because that shows the velocity dispersion of coal gas from which stars are born, and how this velocity dispersion essentially changes with redshift. So you can see that if we look backwards, the dispersion was higher, essentially because there was more gas, there was a higher degree of turbulence, and so the velocity dispersion was higher. So it could also be just that older stars were born hotter. Probably in reality, it's some combination of the two. So back 20 years ago, if we go back to this nice simple plot of the age velocity dispersion relation, you can see if we now look at this sort of steep increase around 9 gig years, the authors, if I just sort of go to the abstract, they attribute this abrupt increase in the stellar velocity dispersions to a minor merger that occurred about 9 gig years ago, which possibly also created the thick disk because there would have been some extant thin disk that existed before this merger occurred. And this heating event essentially puffed up that disk. And we'll come back to this because obviously Gaia has revolutionized understanding of this in quite a dramatic way. So now in the Gaia era, what's really, in my eyes, what's really been revolutionized is not only our ability to characterize the phase space and chemistry, along with spectroscopic surveys, but it's also the age distribution of the stars. And it's really the ages that let us sort of piece together the different events that have occurred in the history of the Milky Way and make some kind of timeline out of it. So the camera on board Gaia, it has 1 billion pixels, and this is about 100 times more than like your best handheld digital camera. And the light is collected on 106 charge-coupled devices. So you have a set of CCDs which are geared towards astrometric information. And so from this you have brightnesses, and this tells us the G-band magnitudes, and then you can analyze how the photometry changes with time, essentially to get an idea on the sky positions, parallaxes, and proper motions. And then you also have some light that is fed into a blue and red photometer. So these provide us with low resolution and broadband prism spectra. And if you integrate the blue and red spectra, you get an idea of the sort of the blue and the red magnitudes. And you can also analyze these spectra using a spectroscopic pipeline to get some idea of stellar parameters. And then the third set of CCDs are essentially feeding the light into the radial velocity spectrometer. So this is medium resolution and narrow band spectra for the brightest stars. And the focus of this instrument is to pick up line of sight velocities for the nearest stars to the sun. And also you can gauge the stellar parameters for these stars as well. So if we just focus on what kind of phase space information that's become available. So this is Gaia DR3 shown here in galactic coordinates, so the bulge is in the center. and you can spot the large Magellanic Cloud and the small Magellanic Cloud. So the phase-space information is, so this is like positions, parallaxes, and proper motions. This has become available for over 1 billion stars, and actually there's almost 2 billion stars with some kind of incomplete set of coordinates similar to the position, parallax, and proper motions, one of them perhaps missing. And this is really remarkable. It's quite a significant percentage of the population of stars in the Milky Way. And now in parallel, what we have back here on Earth are a number of ground-based spectroscopic surveys. So obviously there were some spectra being taken by Gaia, but the ground-based surveys are at, there are many ground-based surveys that are medium or high resolution. And these are able to provide pretty accurate line of sight velocities, spectral parameters with low uncertainties, and perhaps most interestingly, it gives us access to chemical abundances for millions of stars. So obviously not the billions that you have with Gaia, but for millions of stars, which is really still quite a big number. And here I'm just showing, again, in galactic coordinates, so that's the galactic plane, and that's the center of the Milky Way, the kind of coverage for some of the surveys. So these are some of the big surveys. So the two surveys I will talk about later are Apogee and LAMOST. So I'll just point that out here. So you've got Apogee, which is an infrared survey. So it can look into the galactic plane, can see through the dust. And it's looking in the north and the southern part of the sky. And then we have the LAMOST survey, which is lower resolution, but it can probe into the inner halo. I think it has a slightly better distance coverage than Apogee, and a really large number of stars in that sample. Now, what has been remarkable, like with all this, if you put all this data together, is that we've been able to assemble an unprecedented sample of millions of red giants. And red giants are really nice stars, probes of galactic archaeology, because you can see them, they're very bright, so you can see them at large distances. And they also exist at essentially every epoch of the existence of the Milky Way. So, you know, populations of different ages are essentially slicing through time. Now, Gaia and the spectra together can tell us a lot, but what they don't tell us directly is the ages. So this is something that has to be estimated. So what we have over here are some isochrones from Parsec. And these are essentially something that tell us what a star of some age and metallicity and mass looks like in terms of its intrinsic luminosity, given you have some idea of the distance, colors, and spectral parameters like effective temperature, log G, and metallicity. So if you want to determine the age of your star, you essentially try and just find the best isochrone that fits the observations that you have. Now, the problem with red giants is they lie in this region of the isochrones. And what you can see is, so these isochrones are plotted for solar metallicity for a range of ages. And you can see that the isochrones for red giants lie very close together. Now, even before what I'm going to talk about next, actually the access to intrinsic luminosity through the parallax information Gaia has been pretty revolutionary in disentangling or reducing this degeneracy to some extent. But we can also use another bit of information that's really useful. And this is based on work that was shown a few years ago by Mary Matig, who essentially showed that for red giants, they also have an independent piece of information on their masses. And this is from astroseismology data. So these red giants are essentially pulsating, and you can get time series of their photometry to do a Fourier analysis of the pulsations. And the spectrum that you get, so it's like an acoustic spectrum, essentially encodes the mass of the stars. Now, the mass of a red giant is telling you how long that star has spent on the main sequence. So it's essentially telling you the age of the star. Now, Marie showed that you can actually use just a small number of parameters. And the main driver in the set of parameters is the ratio between carbon and nitrogen. This is actually a very good estimator of the mass measured by astroseismology, the much more precise mass measured by astroseismology. So she fitted, I think, a polynomial in this paper. And on the x-axis, you've got the mass predicted by astroseismology, and on the y-axis, the mass predicted by her model. So it fails to some extent at higher masses, but it does a pretty good job overall. So what I did with Jason Sanders, who I think was a postdoc there, who I guess just left recently, is we designed a hybrid approach that essentially tries to put together all these different bits of information. So the core of the approach, so it's like a Bayesian isochrone pipeline, are the stellar isochrones. So you have information on the intrinsic luminosity from the Gaia photometry and parallaxes. You have spectroscopic information, so the vector temperatures, surface gravities, and metallicity from the spectroscopic surveys. And then, so we actually did these for all the stars that lie in the overlap between Gaia and the spectroscopic surveys that I showed earlier. But for the subsample of stars, which are red giants, we created artificial neural networks, so replacing, essentially doing the same thing that Marie Martig's model did, but we did a better job, we did a better job of recovering the high mass end. So including similar kind of parameters. It's a little bit more flexible, it's not a linear model. So I call that here Bayesian spectroscopic mass estimator. And together, we generated a catalogue of about 3 million ages, along with their uncertainties using stellar isochrones. So you can just see the map here. So this is again in galactic coordinates. So the oldest stars are about 9 gigayears, and that's in yellow. And the youngest stars are blue, and it's about 2 gigayears. And so just looking at a map of the ages, you can see a young thin disk, you can see the old thick disk and a halo, and that's the large Magellanic Cloud. So you can even see the star formation that's going on in the large Magellanic Cloud. I know there's been papers looking into that as well. So, so actually just looking at the ages and where they are, it tells you quite a lot about the structure of the Milky Way. And so what you can do is, so actually authors have used this catalogue to do lots of really interesting things, but I'll talk about 2 things that I've been involved in. So essentially interactions with probably satellite galaxies and how they've been key to shaping the phase space, metallicity and age distribution function of the inner halo and outer thin disk of the Milky Way. Now I realize I've said the history of the Milky Way, and it's definitely not the whole history, it's just the part of the history that I've been working on. So I think one really exciting thing that's happened since Gaia is really a confirmation of that prediction back 20 years ago from Killer and Garnett and possibly other authors at that time, that there was some kind of merger probably hiding in our halo. So Nissen and Schuster also since then, so before Gaia, found evidence of stars possibly belonging to this kind of merger in 2012. And then I guess much more dramatically with the Gaia data, a number of authors have shown its existence. So it's now like called the Gaia Enceladus sausage. So Vasily here and other authors essentially looked at the Gaia data within, I think, 10 kiloparsecs and sliced it in terms of metallicity. So the panels going from left to right are different slices of metallicity. So you have the metal porous stars in this panel, and the sort of, it's not actually metal rich, but the metal richer stars in this panel. And then if you look at the V5 component of the velocity vector against the radial velocity component, you can see that the metal rich halo stars are either co-rotating with the sun, or they're on very radially anisotropic orbits. And they essentially attribute this to some massive dwarf galaxy that is embedded in the inner halo, whose orbits have been radialized through experiencing dynamical friction as it entered the Milky Way potential. Other authors, so I just show one example here from Amina Helmi, but there's also been other authors who've worked with a similar data set. They examined the Apogee Gaia data set. So if you remember, Apogee is an infrared survey, spectroscopic survey, for which you have abundances as well. And they looked at the cross match between that and Gaia, for which we have the kinematic information. And they looked at how the stars are distributed in the Milky Way in the plane of alpha over Fe versus Fe. And this is a really interesting plane because so the alpha elements are essentially produced primarily by type 2 supernovae. And these occur very early on after star formation starts. Then after about a gigayear, so these type 2 supernovae, they also produce iron. So that's why, I mean, you can't really see it here, but if you look at the chemical evolution models, you have this sort of plateau early on, which is just because these type 2 supernovae have a constant ratio of alpha elements to iron. And then there's a kind of knee, which is not very well resolved here, So it looks like this essentially, and the point at that occurs is about a gigayears, but there's a distribution at where that occurs, which is when type 1a supernovae start going off, and these essentially produce iron and iron peak elements. And so this is why you start getting this decrease in the alpha over iron. Now, what's interesting is, so you've got metallicity on the x-axis here. The rate at which this iron is increasing in a system depends on how big that system is. So the slope in this plane is an indication of how large the gas reservoir, I guess, in that system is. So that's why you have the thick disk and thin disk lie over here to the right, when all the accreted stars that were probably born in dwarf galaxies lie to the left. It's obviously not quite that simple because the thick disk and thin disk are also separate, but this is essentially an indication of their different star formation histories, which I won't go into so much detail here. But what Amina Helmi and her co-authors did is they looked at the co-rotating stars and looked at where these lay in this plane. And you can see that they're essentially what we would think as accreted stars. Obviously, it's not a pristine accreted population because there's some overlap with the thick disk and thin disk. And the other thing you might note is that the scatter in this direction is quite large. So it's unlikely it's just one system. The reason why I say this, I don't have a plot to show you, but you can also look at Sagittarius, the Large Magellanic Cloud, and some other massive dwarf galaxies that we think are of similar size, or probably not as big, but comparable at least to Gaia Enceladus sausage. And the scatter they have is much narrower. So it's unlikely that this is just one system here. There's probably lots of other stuff there as well. So one thing I wanted to do with so Keith Hawkins and Payel was to try and look at the challenge of how we can define Gaia Enceladus sausage itself, because I mean it's obviously quite difficult to do this. So one thing we explored, which is not necessarily the best way, but I think is quite a promising way, is to just look at abundances, but look at, instead on the y-axis, what we're looking at is the ratio between magnesium and manganese. And magnesium is an example of an alpha element that's produced in the type 2 supernovae early on. And the manganese, unlike iron, it's a pristine tracer of supernova 1a. So it's not really produced in type 2. So this ratio is really like talking about when, so it's comparing the rate of type 2 to type 1a quite purely. And then on the x-axis, we have the abundance, the aluminium over iron abundance ratio, or aluminium enhancement. And this is an interesting ratio to look at because it's generally lower in accreted systems. So what this plane does quite well is it separates the high alpha thick disk stars from the high alpha accreted stars, and the low alpha accreted stars from the low alpha thin disk stars. And then we applied a Gaussian mixture model, obviously making the assumption, which is probably incorrect, that these are Gaussians, but it's a useful tool to use to divide it up into different components. And we essentially attribute this to Gaia Enceladus sausage. And then what you can do is, sorry, I'm just gonna have some water. You can look at the ages of the stars that belong to that component, and that can tell us something about the star formation history, and it can help us date the merger as well. So there are a few lines here. This is age on the x-axis, and it's just distributions. So the red line shows the distribution of Gaia Enceladus sausage stars. And so I should note here that the uncertainties in the age can be up to 30%. So there is going to be some smearing because of that. But I think it still gives us a rough idea of the star. So it's not quite the star formation history because there's a bias induced by the survey selection. But this gives an idea of the range of ages. It's probably the best way to say it in Gaia Enceladus sausage. And it also implies that it merged with the Milky Way probably about 8 gigayears ago. You can also look at an analogy to the plot I showed earlier from Vasili's paper, which was looking at the plane of VR over V phi. You can work out the radial action. So this is a measure of the radial excursions of a star. And so again, in the red line shows what it looks like for Gaia Enceladus sausage. And you can compare it with other metal poor stars. So I think I'm looking at stars metal poorer than -0.8. and they have a much wider distribution when the distribution for what we think is Gaia Enceladus sausage is much narrower. Again, suggesting that it probably experienced something like dynamical friction, which radialized the orbits. And then you can do another simple calculation here, which is look at the width. And this width is essentially a measure of the dispersion, the velocity dispersion of the system, which is a measure of the mass. So just from looking at the width, you can make an estimate of the total mass of Gaia Enceladus sausage, which we find to be about 10 to the 11 solar masses. And I think this agrees somewhat to other estimates that can be made looking at, for example, the star formation history. So moving away from the halo, but actually spatially not so much, because I want to now look at the outer thin disk, and spatially actually overlaps with the inner halo. What we've been learning over maybe the last 10 years or so is actually the outer thin disk. So if you think of the thin disk further in, the inner thin disk, it's probably quite flat, but as you go outwards, it seems to flare. And actually on top of flares, there's also been, people observe warps and observe ripples. There's a nice, this is a nice sort of picture of the warp here. And these are probably all, indications or signatures of interactions with satellite galaxies. And then I'm just going to show here. So this is actually before Gaia became available. This is apogee data, where they've looked at the vertical scale height. So this is just a measure of how far the stars reach above the galactic plane. So I just want to focus your eyes on the bottom panel of plots. So this is looking at low alpha Fe stars. And so these are stars that are defined to be part of the chemical thin disk. And you can see how this vertical scale height increases with radius. And you can see that in the thin disk, essentially increases with radius everywhere, and possibly more so for the metal porous stars. So this is one of the features we've observed in the outer disk, and this is something I wanted to look at in a bit more detail. So a really nice sample for looking, for probing the outer thin disk is the Lamoste Gaia red clump sample. So this is one of the surveys that has a larger sample of stars, mainly because it's lower in resolution. But we still have access to the alpha abundances and the metallicities, as well as all the Gaia kinematics. So if we plot these stars in the plane of alpha over Fe versus metallicity, this is just a density map in this plane. You can see that actually there's a lot of stars that belong to the chemical thin disk. So I think there's about 100,000 stars. So I just made a quite simple sort of distinction between what I thought was the high alpha and the low alpha disk. So I examine essentially this part of the disk in a little bit more detail. So if we look at these stars, just select the stars in the galactic plane. And we just look at how the stars are distributed in terms of their ages and their metallicities. So on the left, you've got the histogram showing how the metallicities are distributed, the alpha abundances and the ages. And then going from top to bottom, this is just looking at all the stars beyond 10 kiloparsec, beyond 12 kiloparsec, beyond 14 and beyond 16. And what you can see as you go further out is there seems to be a component around 6 gigayears, 0.1 alpha and minus 0.6, which appears. I mean, obviously this is not definite evidence for it, but it looks like there might be a component with a sort of narrower age metallity distribution overlaid a component which has a broader distribution in ages and metallicities. Now, this component has obviously been talked about. I don't know if it's exactly the same, because this is actually, I've been looking, these plots are actually in the galactic plane of the Milky Way, but authors have referenced many times in the past the monostrous ring and also the anti-center stream, which is shown quite remarkably here with, I think this is actually Gaia DR3, sorry. So it's just looking at structures. So this is in galactic coordinates, and you can see above the plane that there are these structures. So there's higher density structures over here, and I'm sure, and I think there's also been work by Shevin Lepore, who examined a similar distribution of stars, who finds this component too. But I still wanted to look at this component in more detail because I think it coincides with the flare disk, and I want to see what we can essentially learn from looking at the kinematics as well. So one thing you can notice is, so firstly, people still haven't really understood what the origin of the monostrous ring is, and there's lots of ideas out there. I think probably the most popular is some kind of interaction with a satellite. And I think that makes more sense, because if we look at, so this is a nice plot from Sophia Feltzing from last year, where she essentially had an algorithm for working out which stars in the Milky Way disk had been born there, so hadn't suffered, you know, interactions like radial migration interactions with spiral arms that lead to them sort of their radii being changed. And these stars, which haven't been shuffled around because of radial migration, are a really good indication of what the chemical enrichment of the interstellar medium is. So it's essentially telling you that there's a metallicity gradient, because the inner disk is metal richer than the outer disk, and it tells you there's a gradient with age. So the older stars are metal poorer. Now, if I put this component that we found here, in this diagram, it just belongs in this part of the diagram. So essentially, it has the expected ages and metallicities you'd expect in the outer disk in an inside-out growth scenario. So I think the fact there's some kind of overabundance there is better explained by a star formation enhancement, rather than, I think some of the theories in the past were that it was some kind of dwarf galaxy or a different component. I would have expected the ages and metallicities to look quite different if that were the case. Now, what we have access to with Gaia data is the age velocity dispersion relation. Now, not just looking at the solar neighborhood. If you remember one of the early plots I showed, that looked very simple. We can actually look beyond the solar neighborhood, and it's much more complex. So here on the y-axis, I have the vertical. So I'm just going to look at the vertical component in the velocity dispersion and see how it changes with galactocentric radius. So you can see the inner disk. So this is like for all stars within a slab, which is about 1.5 kiloparsec below and above the plane. And this is for a slab just above and below the plane, but not the galactic plane itself. So you can see in the inner disk, the velocity dispersions increase with radius, kind of like what you would expect as the potential is weaker out there. Also, the older stars are hotter, and this is again because of some of the reasons I explained earlier, either some kind of interaction with spiral arms, or maybe just gas being hotter earlier on. But the outer disk is much more complex. So in the slab that includes the galactic plane, you can see that older stars are constant or perhaps gently rising with radius. And then the younger stars seem to be gently rising here, but actually further up, they seem to be just falling as expected. There seems to be a bit of a gap around 5-6 gigayears in the behavior. So there's obviously something going on with the kinematics and the age metallicity distribution, but it's quite difficult to completely understand what's going on unless we have an idea of what the intrinsic structure is. The problem with these spectroscopic surveys is that they make a selection in color and magnitude. And if you use the isochrones, you can see that maps to quite a complex selection in age, metallicity, and distance. So you really need to account for this to try and understand what the intrinsic distribution out here is. Essentially what you're trying to do is, so this is the function I introduced earlier on. So this is just the distribution of the stars in terms of their positions, their velocities, their metallicities, their alpha abundances and age. And then what you'd like to, what you actually measure though, is the observed distribution in this space. That's actually a product of the intrinsic distribution and a selection bias, which essentially plays a role in the space of distance, metallicity, and age. And there was some work I did with Andy Averill, who's a PhD student there a few years ago, where, well, essentially, I guess Andy demonstrated how you could essentially develop an algorithm to correct for this bias. So here you've got a green line, which shows the intrinsic distribution of distances of stars from the sun. Now, the red line is what you observe. So he developed a package that can essentially recover the intrinsic distribution by accounting for this bias for any kind of spectroscopic survey. Now, fitting this kind of model, you can imagine that a distribution in this space has a lot of parameters. So it is quite useful if you can make an assumption of a dynamical equilibrium, because that essentially ties together your positions and velocities through a gravitational potential. Now, we know out there that it's messy, there's ripples and warps, But is there something, maybe the dispersion, which, you know, is a second component of this moment of this distribution function? Maybe the dispersion could be a reliable indicator that we could use to probe the sort of equilibrium structure. And you can make, and I also try and make a sort of simple, get a simple idea of whether I think this is a reasonable approximation at all by looking at the vertical equilibrium dynamics equation of a 1D slab. And so what you have here is you've got the vertical velocity dispersion profile of the stars in the galactic plane. And this is proportional to your total surface mass density times your scale height, vertical scale height of the stars. Now, I showed earlier that the vertical scale height is approximately proportional to R. The surface mass density, when you have a flat circular velocity curve like you would for a dark matter dominated halo, is proportional to about 1 over R. So you'd actually expect a velocity dispersion component that's constant. And very approximately speaking, this is what I see in the velocity dispersion profile. So again, I'm just saying that this is an approximation I made so that we can recover the intrinsic structure, just as a useful tool for recovering the intrinsic structure of the outer disk. So what I'm showing here is the metallicity distribution, alpha distribution, and age distribution of the stars. So that's shown for the Lamoste red clumps, and that's shown by the gray. So you can see that because of this selection to get red clumps, you actually have a very biased age distribution that's biased towards young stars. And then what I've plotted on top, so in pink, is essentially my two component model. So for the inner disk and the outer disk, I have my intrinsic model, I apply a selection on it to make it look like as if I was observing it in the sky, and I add some errors to it. So that's what I get in pink. And it's not perfect, but it does a decent job. And then what you get in yellow is the intrinsic distribution of my model. So you can see how different it is, especially in this space. In velocity dispersions, it doesn't look very different, but in terms of metallicity and age, it can look very different. So this is not a model I fit using, you know, a fancy Bayesian algorithm or anything, because there's lots of stuff going on the outer disk, and I think you can learn a lot more from just, you know, looking at different models and how they look like in the space of observations. So this is just a model I thought did a reasonable job. And you can see the intrinsic distributions, which is really interesting. So this is implying that this is approximately the star formation history. It's not quite that, because it's only for the stars that have survived to the present day. But it seems like there was, you know, it was high early on, and there was possibly another peak around 6 gigayears. And then if we look at the metallicity distribution, it looks like there's some broad distribution of metallicity, and then there's some kind of peakier component as well, which again suggests some kind of star formation enhancement. Now, if we look at the literature, other authors have also concluded there must have been some kind of accretion event or that led to some kind of star formation enhancement in the outer disk. So this is work by Zhenhun Lian, and there's also another paper by Spitoni, I think, this year. So they're just looking at the chemical evolution. They're not looking at the kinematics at all, and they don't look at the selection bias or anything. So I think, what I didn't say quite quickly is if you look at the data out there, it looks like that component, so what's associated with monosis ring is about -0.6, but actually if you take into account the survey bias, it's actually more like -0.4 is a better indication of the mean metallicity. So they don't take into account this bias, but by fitting their chemical evolution models, they find that there's probably some kind of late time accretion event around, they get a slightly different time from me, around 8 gigayears, which could have led to enhancement star formation and explain the age metallicity distribution out there. And then also from the perspective of cosmological simulation, so there's some really nice work done with Vintakardan, which is a high resolution cosmological simulation where they have a Milky Way like galaxy, and essentially it's fed by 2 separate accretion channels. So you have a filament A, which is feeding the inner disk, which is metal richer, and then a filament B, which is feeding the outer disk. But the filament feeding the outer disk essentially creates a tilted disk. And then over time, because there's a mutual torque between the 2 disks, they do align, but because the potential is weaker out there, the vertical height of the stars is preserved, and as it relaxes over time, this gets it manifests in the dispersion, in a higher dispersion up there as well. So the thing with this scenario is, firstly, you would only expect the stars born in the tilted disk to be hot. And I think I actually find all stars older than 6 GeV to be hotter out there. The other thing is you might expect the age metal structure to look quite different in the outer disk. And I don't think that's the case with the Lumos data anyway. So another possible explanation is sort of motivated by this really lovely plot put together by researchers looking at just the photometry and the photometry data in Gaia. So this is looking at colors and magnitudes. If you're not constrained to the spectroscopic surveys, you have a much more complete sample here of many stars, and you can fit color magnitude diagrams. And they did this, and they got a really, what looks like a really high resolution indication of what the star formation history is. So this is, if you compare to my age distribution that I showed before, it's sort of inverted because it's the look back time goes this way. So they also had like a higher star formation rate in the past, and then some kind of peak at 6 GeV. And then what I don't see obviously with my work, because it's a much smaller sample and there's lots of models that have gone into that, they see these mini bursts at 2 and 1 GeV. And if you compare with, so yeah, I just wanted to show this plot from Eugene Vasiliev, who's in the audience there, work, who's looking at the trajectory of Sagittarius. And so this is again look back time. It's possible that so the points here are the pericentric passages. So when they, when Sagittarius was closest to the Milky Way, it's possible that these coincided with star formation enhancements. And so he only goes back 3 GeV, but it's possible that the enhancement seen here could be a result of some kind of pericentric passage, possibly Sagittarius. And actually, if we go back to the velocity dispersion profiles, the vertical velocity dispersion profiles that I showed earlier, it does seem around 6 GeV is where there's this increase if you look above and below the disk. Now, so this is where I get very hypothetical because this is work really that I'm doing at the moment. I wanted to make just a simple toy model to look at how Sagittarius would impact the vertical velocity dispersion. So what you can do is, if we assume that the impact of Sagittarius is essentially very quick, so we can ignore the external forces on the stars in the outer disk, so this, the forces exerted by the other stars and the rest of the Milky Way. We assume they're small compared to some large but brief force that's exerted by the perturber Sagittarius, for example. We can make something called an impulse approximation, so where we only really care about the point of closest approach and the velocity at the point of closest approach. Now, if we assume that Sagittarius can be well explained by a plumosphere in its distribution of stars, this is actually something that reduces very easily. So this is essentially telling us what kind of kick the stars feel in each component. And it's related to the mass of Sagittarius. So obviously, the bigger the mass, the greater the kick. It's related to the relative distance. So yeah, this is a bit complex because the magnitude is what's important because that's squared there. And it's also related to the relative velocity. So the lower the velocity, the longer I think it feels the impact, which is why the bigger the kick. So just by using this simple toy model, I could use my distribution function model. Essentially tells me what the inner disk and outer disk look like. So I sort of just take the outer disk away, assume the outer disk look like the continuation of the inner disk, and then I calculate what the kicks would be from Sagittarius approaching in the way it did last time. So just using the parameters from Eugene Vasiliev's work. And then you can apply these kicks, and then you can evolve the system for a few dynamical timescales to see what the dispersions look like. And so that's what I've done here. So on the left, it's the vertical velocity dispersion again, what it looks like in my model before Sagittarius came along, and then what it looked like if Sagittarius impacted 6 GeV ago in a very similar way. Now, you can see that basically there's hardly any change. So this is really now work that I'm doing now, which is we know that the impact if there were an impact about 6 gigayears ago, it would have looked very different. So already in Eugene's work, he showed just by looking at how Sagittarius is being disrupted tidally as it goes around the Milky Way, that its change in mass is of order 10 to 20 within 3 gigayears. So you can imagine it must have lost a lot more mass. So what I'm basically exploring now is, can I say something from the way the vertical velocity dispersion looks like now? Can I say something about a potential impact with Sagittarius 6 gigayears ago, how big it was, and from how it affects the profile, it obviously affects it differently here from over here. Can I say something about where it was at the time of impact? And yeah, so looking towards external galaxies, actually you have a lot of similar information that we have from Milky Way. So this is a set of galaxy Milky Way analogues from the Mangia survey. And it'll be really interesting to know what we can learn about the heating history for these galaxies and how they compare with the Milky Way. So obviously we can't do the same kind of detailed work we've done for the Milky Way, because what we have is an idea of the light and the ages, not individual stars, but stars along your line of sight. But I think there's enough information there to say if there's something very different going on in the outer disk and the inner disk, and perhaps we can date this as well. And this is, yeah, work that Rob Yates, who's a postdoc in the group, is doing at the moment, and I'm looking forward to seeing what he'll find. So yeah, so just to summarize, Gaia and ground-based spectroscopic surveys have really revolutionized how we understand the phase-based metallicity age distribution of stars, not just near our sun, but looking further into the halo and the outer disk. And it's likely that satellite interactions have played quite an important role in shaping those components of the Milky Way. Yeah, thanks very much. I'll take questions.